First of all, before I start my lecture, I would like to thank the organizers, ProSim, especially Dr. Shyam Sundar, for having given me this opportunity to present whatever the works we are doing at NAL in the area of dynamic and aeroelastic analysis of aerospace structures. In fact, I would like to specially thank my guru, Professor Manohar. In fact, his lecture preceding my lecture has helped me in presenting my lecture in a much easier way, because he has touched upon some of the fundamentals of the topics which I'll be presenting as we go on with my presentation, particularly on some system identification related issues. A brief introduction for those who are not initiated to this topic. Basically, these are the main parts of, basically an aircraft consists of a fuselage, wings and the VT. These are the engine actually. And coming to the topic of our interest, when it comes to the rigid body motion, it will be having three major degrees of freedom, which we call them as the rolling, pitching and yawing, apart from the translational motions. So they are indicated in this picture, because these are some of the degrees of freedom which we will be dealing with as we proceed. Apart from that, we will be having a lot of elastic degrees of freedom. Coming to the topic of aeroelasticity, because most of you are introduced to dynamics by now. Coming to the concept of aeroelasticity, see, basically we have inertial forces, we have the elastic forces and the aerodynamic forces which come into picture when we are dealing with aircraft structures. Now, if we treat these three forces, and if we consider the interaction between the inertial forces and the elastic forces, that leads to what are known as the regular vibration problems. And the interaction between the inertial forces and aerodynamic forces leads us to the problem of stability and control of aircrafts. And the interaction between the elastic forces and aerodynamic forces, that leads to what are known as static aeroelastic problems. And when all the three they are interacting, then it leads to the problem of dynamic aeroelasticity. Now, in static aeroelasticity, we encounter several situations. One of the major situation is the divergence problem. The divergence problem, it is a static instability problem, wherein with the increased velocity or the airflow, there is going to be a static instability in the aircraft system, and there is going to be increased deflections. And there is also going to be the phenomena of control surface reversal that takes place when under the static aeroelastic problems. Okay. Now, coming to the dynamic aeroelastic problems, there are issues known as flutter. Flutter is again a dynamic instability problem. Here what happens is, with the increased aircraft speeds, okay, there is going to be a dynamic instability issue that is coming into picture, wherein there is going to be increased amplitude of vibrations of the aircraft. So that leads to the phenomena of flutter. There are other issues such as the buffeting and aeroelastic gust, and several other related dynamic aeroelastic problems are also encountered in the field of aeroelasticity. Now, the flutter problem, I am just trying to show them with a few pictures here. When a system is subjected to dynamic loads, in the normal conditions, there is going to be a regular damping. Okay, they are called the damped vibration problems. In the damped vibration problems, what is happening is, under damping, there is going to be a gradual decrease in the amplitude of vibration, like what we are seeing in picture number 1. So then, at flutter condition, what happens is, there is going to be a constant amplitude vibration that is going to set in. It is going to be something like this. And beyond the flutter condition, beyond the flutter speed, there is going to be a increased amplitude of vibration. That means that is going to lead to a catastrophic failure of the aircraft. The similar conditions are also encountered in case of civil engineering structures such as bridges. I have a few animations which I can probably show here. This is the aircraft tail boom flutter. So you can see that the tail boom there is a flutter condition that is resulting here. You can see that, this portion. Then we also have what is known as aircraft HT flutter. HT is nothing but horizontal tail. You can see that. Then similarly we have what are known as aircraft vertical tail flutter. Then we have aircraft wing flutter, which is I was calling as divergence. It's a lab model. Also, we have some computer simulation movies on the aircraft flutter. Of course, it is over animated. Please don't get carried away by that. So then we have Takamo-Nares bridge flutter. Okay, there is another view of this. I think this many of you might have seen in the net also.
The car had been abandoned earlier. No one was injured in the whole affair. However, a small dog in the car was frightened and was afraid to come out, and he perished along with the bridge.
Okay. So this is something about the phenomena of flutter, what we generally encounter in case of long span bridges and also in case of aircrafts. Okay. And in today's talk, most of the topics, most of the methods what I will be talking about and most of the problems what I will be presenting are related to this, the so-called phenomena of flutter. Okay. Coming to the methods of analysis of flutter. There are many methods are available. So basically I have tried to classify them in terms of the kind of difficulties we encounter in handling those problems. So one of the most basic method that we have is the classical method, wherein it deals with these systems where the structural damping is not considered. Okay? It is the direct method of solving the complex eigenvalue problem. This method can be very conveniently used in case of simple problems like 2 degree of freedom systems or maximum 3 degree of freedom systems. But nevertheless, it is a very useful method for doing research problem, for solving the research problems. Then we have the next method, which are known as the state space method. It is a numerical method. Generally, it is an iterative method which can handle problems with large degrees of freedom. Okay? And generally, this is one of the most popularly used method of computing flutter in the practical problems. Then we have the next class of problems, which are known as the time domain simulation. In time domain simulation, again we have different grades of problems. In time domain simulation, what we are trying to do is we are trying to simultaneously solve the equation of dynamic equilibrium on the structural side and the aerodynamic equations on the aerodynamic side. Then again, depending upon the complexity of the aerodynamic model that is considered, the methods keep getting complicated. It starts with the simple assumed lift gradient for aerodynamics and it can proceed up to the use of the complex Navier-Stokes equations or the Euler's equations to be solved. Then we also have other methods which are known as the flutter prediction using experimental model parameters from GVT. This method is very closely related to the system identification methods what Professor Manohar was talking just in the previous lecture. Then we also have what are known as flutter prediction methods based upon operational model parameters, okay, using flight flutter tests. And last but not the least, we also have flutter prediction techniques using the wind tunnel testing. These are the various methods which we generally use for computing the flutter speeds of the aircrafts. Now, coming to the comparison of the methods, I was telling you we have the most simplest classical method which goes right, which can consider simple aerodynamics for modeling, and it is much easier for hand calculations. It goes up to the most numerically robust and high fidelity method of using Navier-Stokes equations for the aerodynamics coupled with the finite element method for the structural modeling. Again, there are two variants in this. One is when we don't consider the effects of viscosity, we use what are known as the Euler's method. Okay? Otherwise, it will be a full-fledged Navier-Stokes method. In between, we have the state space method and the methods of using panel methods. When we use panel methods, we also use some corrections for compressibility corrections, then unsteady, corrections for unsteady effects, and so on. So in time, generally we use what are known as Theodorson's corrections. We also use Wagner's corrections, and so on. Now, coming to the solution approaches, we have what are known as the eigenvalue approaches, which are used in the classical methods as well as the state space methods. And coming to the time domain approaches, wherein we use the Newmark's techniques, we use the finite difference techniques, and all these high fidelity techniques of solving the equations we use here. Now, considering the simplest method, that is the model thing, we just model the given a simple airfoil like this will be considered with here we are considered the airfoil with 2 degrees of freedom, that is one is heaving degree of freedom, the other one is pitching degree of freedom. That is why in the very first slide I showed that what are the kind of a freedom we encounter. Okay? Then the basic equations are set like this. It is a basic equation of motion where damping is not considered. Then we go ahead and set up the equation in terms of a determinant like this. Then once we solve this, we consider that the flutter occurs when the lambda r is, that is the real part of the lambda is greater than 0. So this is a very simplest way of solving the flutter equations. Okay? Here the imaginary part, it represents the frequency, and the real part represents the damping. When the damping crosses 0, we assume that the flutter has occurred. This is a simple slide which shows the effect of masses on a given thing, like what happens when a mass is moved towards the rear, how in the case of airfoil, it produces additional inertia moment and it acts against the stability, leading to earlier occurrence of the flutter. This is one of the parametric studies which we did with this work. Then in the state space method, what happens is we have the same equation of motion, but we also have the dynamic, damping component here. The damping here consists of not just the structural damping, it also involves the aerodynamic damping. And even if you neglect the structural damping, aerodynamic damping is always going to be present. Then the system of equations is transformed into a state space form by doing this substitution, where S is given by this matrix. It goes through a series of steps like this. Ultimately, again, we get into eigenvalue problem like this. We also apply what are known as the Theodorson's complex function for considering the unsteady effects. Then we solve these equations in an iterative way. The iterative algorithm is indicated here. There are various methods again. There are what are known as the P method, K method, PK method, and so many methods are available in the literature. But the most popular one is the PK method of solving the equations. Then the equation is solved in an iterative way till the convergence is reached and till we obtain the flutter speeds. Then we have the other next class of problem methods what are known as flutter prediction using time domain approaches. This is what I was telling. I was telling it is one of the most high fidelity methods that are available, which makes use of all the methods like the finite element method, finite difference method, all the methods available to us. Such methods are used that can be used in this approach. The basic motivation for, in fact, a lot of groundwork was made in our division for developing methods around this, and the basic interest and motivation for developing these methods was most of the classical methods, and which are also available in various software tools like Nastan and all. They solve the flutter problem in the modal domain, and they are all effective in solving the aeroelastic problems in the subsonic and the supersonic regime. The aerodynamic models available there, the solution techniques available there, they are all good for subsonic and supersonic regimes. But there are no effective methods available for the transonic regime, where we encounter really a nonlinear aerodynamic phenomena. Then we also encounter what are known as transonic dip and so on. In order to predict such characteristics, we started looking at these methods. Okay, so basically, this time domain techniques we started developing for computing the flutter speeds in the region of transonic and supersonic regimes. Here is a case where we are trying to use the time domain approach for an airfoil problem like what I showed you earlier. We tried to use it for computing the transonic dip in the airfoil. Basically, we have used an Euler solver. That means it's not viscous effects are neglected here. The equation of motion is shown indicated here. It is a fully loaded equation of motion. There is no any approximation like neglecting that, neglecting this. Everything is available. Only thing, it is a 2D problem. Okay, because the airfoil problem, it is a 2-dimensional problem. Then we go through the numerous iterative algorithm for computing, for solving this equation, and M represents the mass, C represents the damping, system damping. Various system damping models can be used. Then K represents the stiffness, but the real issue is about F. In all the earlier, this F can come from either the panel methods, like simple panel methods to begin with, and we can use the whole complex Navier-Stokes equation to dump the complete aerodynamic loads calculated from aerodynamics onto this equation of motion. So that is one of the most time consuming and complex problems to solve with. I will be showing some of those pictures later. Okay, see, they are the terms related to aerodynamics again. Okay, here we get what are known as aerodynamic inertia, aerodynamic stiffness, aerodynamic damping. All those things are put here. Okay. So this is what I was talking about, the fluid solver. So here basically we use the unsteady Navier-Stokes equation in a 2-dimensional format, which takes into account the conservation of mass, conservation of momentum, and the conservation of energy. In fact, CFD itself is a field by itself. Most of you know that. Just like we structural engineers are busy with solving our equations of dynamic equilibrium, there is a whole set of expertise available for solving the Navier-Stokes equation. In this method, the so-called method of fluid structure interaction, we are trying to combine the solution of Navier-Stokes equation with the solution of the equations of motion. And the final product of any Navier-Stokes equation solution is we get the pressure. From pressure we calculate the loads, and that load becomes the RHS. And the whole problem is solved. See, there are again closely coupled way of solving, loosely coupled way of solving these equations. Generally, we are trying to do it in a closely coupled way. Closely coupled means the two equations are combined. The Navier-Stokes equation and the dynamic equations of equilibrium, they combined and they try to solve it. In fact, people have tried with limited success for applying to the practical problems, whereas here it is much more easier, but it takes little more time. But with the present days computational facilities available, I think it can be easily achieved. Okay. So this is the algorithm I was talking about. We are talking about partitioned approach or the loosely coupled approach for solving the fluid structure coupling problems. Some numerical results, like using this method we have tried to solve the problem of an airfoil. What I am trying to present here is some of the simpler problems in the first phase of the presentation. Later I will be talking about the actual applications where we are trying to use these concepts for solving the real-time problems. So we are trying to use it in the range, a Mach range of 0.7 to 0.9, which is the real transonic regime. Okay. So this is the CFT mesh that we have used for solving the problem. And coming to the structure, there is no any finite element mesh required here because it is a simple 2 degree of freedom airfoil that we are considering here. Okay. Yeah. So this is the animation. What we are seeing is it is the fluid structure interaction animation. What you are seeing, the simultaneously the fluid as well as the structural equations are being solved, and we are trying to get the end product is we are getting to trying to get the displacement time history of the airfoil. Okay. This is done at different Mach numbers, and ultimately from displacement time history we calculate what are known as the flutter indices. Okay, it is again the repetition of the same thing for different Mach number conditions. The final result is presented here in a nutshell. What we do is we do such fluid structure interaction studies for a range of Mach numbers and for a given number for a range of velocities and various other fluid parameters. We do that, and for each Mach number we come out with what is known as a speed at which the flutter occurs, that is called the flutter speed, and from that flutter speed that is computed for each Mach number we compute what is known as the flutter index. Here we are computing flutter index because in the literature reported they are giving the results in terms of flutter index. There is nothing prevents us from giving the flutter speed directly, nothing prevents us from plotting flutter speed directly along the y-axis. You can see a strange phenomena that is happening here. As the Mach number is increasing, okay, the flutter speed which was around flutter index which was around 1.25 something like that here, there is a gradual dip in that. Then there is a rise for this particular problem. It is not a generalized thing for this particular problem. Then it reaches up to 2.5 something at Mach numbers of 0.89 or something like that. Then again it drops down. That is what the range in which we have the results. Now, this phenomena is called as the transonic dip phenomena. This is one of the important phenomena in the flutter analysis. For capturing this, it is not easy. With the conventional methods of classical methods, it is not possible to capture that. We have to use high fidelity tools like fluid structure interaction solutions like what I was talking now to capture this dip. And also you can see for a given Mach number, there are 3 flutter points that are observed here. This also is not easy to capture using the general conventional flutter analysis techniques like the classical technique or the state space approach. It is only through high fidelity methods like this you can capture this. So this is the speciality of these kind of techniques. Sorry. Now, let us look at the next problem what we are trying to solve. It is a transonic flutter prediction of a swept back plate. Now, from a single airfoil, we are moving to a actual wing-like structure, that is a plate kind of a structure, which in essence it represents the wing or VT what we encounter in the aircrafts, or it can even be the bridge deck. Again, here what happens is the Navier-Stokes equation is in terms of 3 coordinates. That is where the equations change. Here we are considering the total 3-dimensional aerodynamic domain for modeling, and again we have all the mass, momentum and energy terms here. This is the regular aerodynamic equations, and we couple the two and solve. This is again the algorithm that is used. On one side we have the CFT code with the complex finite difference grid. The other side we have the finite element code. Earlier we didn't have the finite element code. Here we do have a finite element code. The finite element method calculates the displacements which goes as input to the finite difference method of solving the aerodynamics. The aerodynamic equations are solved from which pressures are obtained, which are converted into forces, which is given as input to the finite element method. Okay? This goes on iteratively online, and ultimately we get the complete displacement time history curves like what we showed earlier. This is the problem, is a swept back plate which essentially represents the kind of a wing what we encounter. Various studies, first we do a free vibration analysis, in aerodynamic terminology they call it as wind off. Then we also do unsteady flow analysis. Again, in aerodynamic terminology, they call it a forced oscillation, wind on, so on. These two are a regular thing for doing the checking of our vibration modes, frequencies and other things. First one is done to see that our finite element model is fine and we are getting all the frequencies properly. The second one is done to see to it that the flow analysis is done to see to it that all the pressure coefficients and other things what our code is computing is fine. It is in line with our expectation. Then we do the nonlinear finite element fluid structure interaction analysis. Then here for comparison we have also done linear fluid structure interaction analysis. Linear fluid structure interaction analysis is nothing but we have used our regular code like Nastran, which can do a regular transient dynamic analysis using the simple finite element aerodynamic codes like the panel methods and other things. But it's a linear aerodynamic thing. Just to give a comparison, we have also solved using that. The results will show the difference. These are the free vibration mode shapes. Then these are the finite difference grid that is used for modeling the CFD. These are the time histories that are obtained from which the flutter index is computed. Actually, there is an animation here also. You can see that there is in the time domain there is a time mystic that is being computed. That means aerodynamic equations as well as the structural equations are simultaneously being solved. Okay. Then similarly, I told you about linear fluid structure interaction analysis using conventional codes available, conventional PK method and other methods what I discussed earlier. Then here we have plotted for different Mach numbers what is the flutter index. This is what that is predicted by our conventional linear aerodynamics code based analysis like PK method or whatever it is. Then this is what is predicted using our Navier-Stokes method. Here it is not the Euler's method that is used, I think it is the Navier-Stokes method that is used. You can see there is a huge difference. If I predict this as my flutter speed, it is quite high, but the actual flutter speed is here, and that too this happens in the transonic regime. The difference comes up in the transonic regime. So it is this particular phenomena which we are able to successfully capture using the fluid structure interaction analysis. Okay, I already told the observations. Similarly, we have done the supersonic flutter prediction for the same swept-back plate. Okay, this is the finite element model, natural frequency and so on. This is the time history and other things that are plotted. And we have computed using the present method and compared with those obtained through the experiments. Here, of course, instead of flutter index, they have given the results in terms of what is known as stiffness altitude parameter, and we have tried to compute the same thing and give it. It's all the same. Ultimately, we are interested in flutter speed. That we should remember. Okay, this is one set of methods. We have seen two set of methods till now. One is the conventional simple linear aerodynamics based methods like the classical method, the state space method and the related applications. Next we saw the high fidelity methods by combining the finite element method. Of course, in the state space method everywhere finite element method is used, but the aerodynamics that is used is very simple. Then we saw the time domain methods wherein we tried to combine the Navier-Stokes equations with the equations of dynamic equilibrium and solve that. Then we have the third set of methods. They are called as what are known as the system identification based methods. Here, why should we use this method? The question is that most of the time in practice we encounter problems wherein the system related information is just not available. Professor Manohar was talking about the bridge problems wherein the bridges were built maybe 180 decades ago, and today they are trying to requalify the bridges for different new loads and new operating conditions. Same thing is encountered in case of aircrafts. Our Air Force has got hundreds of aircrafts like Jaguar, Mirage and so on, which are all bought in hundreds by spending crores of rupees, and many of them they have flown for about 10 years, 15 years, 20 years, and today they are still continuing to fly. But there is a catch here. The aircrafts, when they were bought, they were qualified for one set of missiles and stores and bombs that they were supposed to be carrying. But today, they cannot be carrying the same missiles and old missiles and this thing. Today, they must be carrying the state-of-the-art weapons. Now, when these aircrafts have to be requalified for the new set of weapons, how do we do that? because the moment the weapons and stores are loaded onto the aircraft property changes. And once the aircraft property changes, it has to be requalified. Otherwise, certifying agencies will not allow the aircraft to be flown. Okay, how do we do that? We don't have the design drawings. They are all imported aircrafts. The OEM will not give us the design details, but still we have to qualify. That is where such methods will be useful to us. Okay, what we do is we indirectly identify the system through tests, and on the identified systems we put the new weapons and we requalify the aircrafts. Now that is the motivation here. One is to access we don't have structural or material details access, so we have to requalify them. This was a byproduct. I'll tell you, we started the effect of loading and unloading the stores. That is another thing. Of course, the byproduct is in the context of FSI. That I'll be coming to that later. Okay. Now, how do we do that? Here is the basic algorithm that is shown. What we do is we conduct laser scanning of the structure that is to be studied. We create the complete geometric model of that. Then we create the once we have we actually go to the equipment or go to the aircraft. We do what are known as the vibration studies on that. We instrument the aircraft. We do the vibration studies. We capture the complete eigenvalues and eigenvectors, the mode shapes and frequencies, everything. Then from that, whatever the eigenvalues and eigenvectors that are obtained, and from the geometry of the aircraft that is developed, we try to develop an approximate finite element model by using certain assumed values of material parameters and other things. After doing that, we get the eigenvalues and eigenvectors. From whatever we get from the experiments, we take that and we replace the eigenvalues and eigenvectors obtained from the finite element model by those values. Then we go ahead and do the analysis. Here is a simple example. This is a simple plate representing a kind of a wing kind of a problem. What we did, first, in order to establish the method, some of these techniques were, some of these tests were done in the lab. Actually, we started doing this on an experimental basis to develop the basic capabilities. And later, see, what happens is, we have the impulse hammer, we do all the vibration test on that, we capture the vibration characteristics. Then we do whatever the grid we use for capturing the vibration characteristics, same grid we use for doing the finite element model also. Then we get some kind of eigenvalues and eigenvectors for that. That will be replaced with whatever we obtain from this. Then we get a finite element model which actually mimics the actual structural behavior. On that, we do all other studies. Okay. So this is a finite element model. These are all the mode shapes that are obtained. This is the finite element analysis mode shapes after replacement. Then once we get the finite element model ready for our which can do the vibration analysis and which can mimic the eigenvalues and eigenvectors, we impose the aerodynamics on that, whatever the aerodynamic model we have, and then we do the flutter analysis. Okay. In flutter analysis, we use what are known as VG and VF graphs for identifying the flutter conditions. VG is nothing but velocity versus damping, and VF is nothing but velocity versus frequency. Okay, these are all some of the results, like how we are using plate formulations, beam element formulations. We are trying to use various methods to see to it that whatever the method basically we developed, that is benchmarked and that is working well. Still, till now I was in the conceptual stage, in the sense I didn't go to the equation level of presenting the methods, although that has also been done to see to it that all the methods whatever we developed, they are all benchmarked. By the end of this, we are ready with the basic techniques, okay, basic techniques that are required for applying for the actual aircraft problem. Now, whatever the methods, whether it is the classical method, the state space method, or the fluid structure interaction method, or even the GVT based flutter prediction techniques, these methods we have sufficient good strength in the division, wherein we are trying to use these for qualifying various aircrafts and supporting various aircraft programs in the country. These are some of the aircrafts for which we use these techniques: the Tejas aircraft, Hansa aircraft, Saras. Then we do have we have also worked on the RLV. In fact, I am proud to say that we were the first to do the, as soon as the basic preliminary design of the RLV was done, that was given to us for doing the finite element modeling and simulations, to give them the feedback on the on the design that was done. Okay, this was done by us during 2006, and I'm happy that 10 years down the lane, 1 week back, the aircraft, the RLV has flown, and successfully it has flown. So we did the finite element modeling and Flutter analysis, everything for that. In fact, the RLV had a different kind of problems. Okay, when I come to that, I will be talking about that. Now coming to the Cirrus aircraft, here for Cirrus, I will be showing the finite element methods that we used, because Cirrus was our own program. We had all the design details, geometry details, everything available to us. We started off doing the finite element model of that. The complete finite element model was developed in-house. Okay, these are all the models for the various components, and the final finite element model of the Cirrus aircraft is shown here. Then we did the dynamic analysis, and also we also did the ground vibration test of that. Once we do the finite element analysis, what happens is we get the mode shapes and frequencies. Then once the aircraft, based upon that, the whole aircraft was fabricated, and then we also did the ground vibration test on that. The finite element model was tuned up depending upon whatever the frequencies and mode shapes that we obtained. Okay, then once the tuned up finite element model was available, this is the ground vibration setup of the Cirrus aircraft. I think we also had, this is based upon the ground vibration test. Okay, so these are the GVT obtained frequencies and more frequencies, and these were the FEM obtained frequencies. Wherever tuning up was required, model updating was required, like what Professor Manohar was telling. Of course, here the problems are one way simple, because we are talking in terms of linear structures, but when it comes to nonlinear structures, problems get complicated. And when we talk about uncertainties, then all those Bayesian techniques and all those techniques will come into picture. So once the finite element model was tuned up, then we used it for doing our Flutter analysis. This is the aerodynamic model that was used. Basically, a panel method has been used here. See, here you can see the red color is the our blue color is the finite element model, and red color is the panel that is used for defining the aerodynamics. Once we combine these two models, we spline the two, so that the aerodynamic forces are transferred effectively to the aircraft finite element model, and the of course, it is one-way flow here, because we are using, it's not a fluid structure interaction kind of a thing, it is a panel methods where it is a one-way. The panel methods are used for computing the loads, and it is given to the aircraft. There the corrections are applied for the changing conditions. These are the VGVF plots, like what I was talking earlier. Using the VGVF plots, we try to determine what are the flutter speeds. Similarly, we have done a similar exercise. Of course, here still we are not doing the GVT based flutter prediction, because we already have all the design details, everything is available, but we are doing the GVT based fine tuning of the model. Okay. Same thing we have for the Hansa aircraft. This is the finite element model, various components. Then we also done the ground vibration test for that. Okay. So based upon the GVT, we get what are known as the mode shapes and frequencies. Ultimately, this is the comparison of the finite element frequencies, then the GVT frequencies, and the damping obtained from the GVT. One of the important information we obtain from GVT is the damping. Then these are the flutter plots in terms of a VG plot and VF plot, using which we predict the flutter speeds. And one more interesting thing about the Hansa is we also have conducted the flight flutter tests using Hansa. That is the third mode of computing the flutter speeds, wherein the aircraft is flown very close to the flutter speeds, and we are trying to capture the VGVF graphs. The aircraft is actually instrumented, it is flown, but we cannot actually touch the flutter speeds, because for the obvious reasons that the aircraft will suffer failure. So we did compute the flutter speeds using flight flutter tests, and the trend obtained using NASTAN and flight flutter tests were observed to be very close. This is all about aerodynamic damping and other things that is computed both using NASTAN as well as the flight flutter tests. Although I cannot name, I can name what is there. We have done it for Jaguar aircraft and Mirage aircraft, and because there the no field data, no finite element model or design data was available, we entirely depended on our GVT based techniques, and we could qualify those aircraft for different kind of a new stores with for the flutter conditions. Then, as a byproduct of the fluid structure interaction studies capabilities, whatever we were developing, what happened? See, once the Air Force got convinced about our capabilities in terms of clearing their aircraft for flutter, they also wanted to look at clearing the aircrafts for stores release trajectories. So, the stores release trajectories, it involves several series of studies, that is in terms of similarity studies, then in terms of doing the studies using the CFD based simulations, then also doing some wind tunnel tests, and also doing the actual flight, releasing the stores under the actual flight conditions. Since we had expertise in all the related fields, and also through these capabilities developed using fluid structure interaction, we also had the capability of doing a fluid structure and interaction analysis. We took up the project, and that was a very interesting exercise that came up as a byproduct of our developing FSI capabilities for flutter calculations. The stores release work, it involves actually solving the 6 DOF equations, that is the rigid body degrees of freedom, those equations coupled with the aerodynamic equations. Okay? So, that we were able to do that, and we were able to predict the trajectories of various kinds of stores using the FSI capabilities what we developed. And another field of expertise that we could develop and use was for computing the flutter characteristics of the propeller blade. That is what we come across what are known as whirl flutter conditions. So, we were able to use some of these techniques for qualifying the propeller blades from the whirl flutter conditions. So, these are all some of the works probably which I should have presented had the slides were working. Yeah, please. Yeah, buffeting generally we are not using any computational techniques for qualifying that. What we are doing is mostly we are qualifying the buffeting conditions through tests, through wind tunnel tests. We are not used, as of now, we have not used any simulation techniques or analytical techniques for qualifying that. But we do have facilities for conducting buffeting thing in our laboratory. We have used those facilities and qualified.
The state space method we can use for supersonic also?
State space method?
Can be output for supersonic?
Yeah, it is used. It is used for supersonic also. See, ultimately those methods they work, but what matters is what is the aerodynamics we use with. In subsonic and supersonic, we can use the simple panel methods, that is potential based methods, and we can solve the equations. We get reasonably good results. But in the transonic regime, those aerodynamic models will not work, and we have to depend on high fidelity models like our Navier-Stokes methods or Euler's methods, or there are some special panel methods which are developed of late. People are using those things also. Yeah.
Your models, the engine is not accounted for. Especially, let us take an example of the propeller engine. It definitely obscures the pressure distribution on the wing. So, does it affect the flutter?
No, the engine is modeled in terms of its mass characteristics. It is definitely modeled in terms of its, we will have a lumped mass sitting there. The flutter characteristics of the engine itself is looked at in a different way. See, for example, the geometry of the engine is accounted for in the models. Okay, the nacelle, everything is modeled. So that generally affects the aerodynamic flow, and that is all accounted. And also the mass of the engine is accounted in the finite element model in terms of lumped mass and so on. Now coming to the looking at the flutter characteristics of the engine per se, that's what I was talking about, the whirl flutter conditions. So that we look at it independently, and we qualify the engine for whirl flutter conditions, particularly the propeller based kind of things separately. So when we are looking at the flutter characteristics of the aircraft structure, we don't combine the engine thing with that. Okay, but we definitely look at it. Okay, let us quickly, this is the RLB design details. These are the design details which were obtained in 2006, based upon which we did the, I'll try to go quickly since I have already briefed. This is the actual vehicle, re-entry vehicle, and this is the booster fin. Booster fin we modeled using a stick model because we didn't have a complete 3D details. The RLV vehicle we modeled using the regular 3D models. This is a finite element model of the RLV. So various modeling details, and these were the final mass CG that we obtained through finite element model and as well as the design values. There was a reasonably good accuracy in terms of FE modeling. Then these were the various frequencies which we computed through our FE model. Later, I think 2 years back, they did the GVT on that, and we compared those values with what we obtained at that time. Of course, there were a lot of design changes after that. Within the, after accommodating for all those design changes, they were all well, they were comparing well. So these are the finite element models. These are the aerodynamic model that was used. In fact, RLV there was a challenge. Most of the commercial tools what we had, they were able to capture the flutter characteristics maximum only up to 2 Mach, 2.5 Mach, 3 Mach. In fact, RLV was going up to 5 Mach and 6 Mach. Okay. In fact, even today, I think that at those Mach numbers they have qualified only through wind tunnel testing. We don't have tools, but today we have the FSI tools like what I was talking about. We are trying to see whether those tools can be used when they come up with the next generation of RLV vehicles. These are all the various boat shapes. So these are the VGVF plot. See in the RLV we have both the ascent phase flutter analysis, whereas during the ascent phase we have both the booster and the RLV vehicle sitting together. In the descent phase we have only the vehicle coming down, it re-enters the atmosphere and it comes down like an aircraft. In both the conditions we plotted both the VG and VF plot, and it was clearing the flutter speed. These are all the various results which we obtained. Then coming to the next set of fighter aircrafts, like what I was telling, the Air Force has got a lot of fighter aircrafts which need to be qualified for the new set of missiles and stores, and they approached us. This is the Jaguar aircraft what you are seeing. This we completed about 3 years back, and after that, based upon the experience, the confidence they gained, they have come back to us for the Mirage aircraft qualification now, because that is going through the major stores upgradation program right now. So this is the setup of the GVT. This is the aircraft which was specially made available to us at IISc in Bangalore. It was flown to our requirement. It was placed here for about a week or so. During that period, we conducted all the GVT on that. These are all the GVT based. This is the GVT based model, that is the to capture the eigenvalues and eigenvectors. Then this is the corresponding FEM model what we developed, corresponding to this grid. Then we used our GVT based prediction technique, and ultimately we could, I think there is a animation here. So these are the stores, and this is the wing, and this is the aircraft finite element model what we have developed. And that is the clean, this is the aerodynamic model for the clean configuration. This is the aerodynamic model for the configuration with the fuel and the stores and all. This is again just to check the splining conditions between the aircraft and the aerodynamic model. And these are the we use PK method here, and these are the VGVF plots using which we qualified the aircraft. So this is a classical case where we have not used FEM model developed based upon the design parameters. It is a FEM model based upon the GVT parameters, and based upon that we qualified the aircraft. Then I was talking about the store separation analysis. Here we have used the fluid structure interaction technique, whatever I was explaining earlier. So these are the stores that are attached to the wing. This is the CFT model that we have done. It is unsteady aerodynamic flow simulations coupled with the 6-DOF equation solver that we have used. This to start with we used with single store, where we obtained the trajectories. This is the multiple store configuration, where multiple stores will be sitting on the aircraft, and various parameters. These are the trajectories predicted by that. Yeah, I think here you can see that. Actually, it won't fall like that. The fall is very smooth. Here, the animation somehow it is coming like that. So that correspondingly, you can see the trajectory also coming up here. This is the trajectory actually. Then these are the various. You can see that this is a fluid structure interaction problem solution is used for predicting the trajectories here. This is one of the other stores that was released. In fact, after release, it turns back and it just moves backwards. I am not naming the missiles here because of confidentiality reasons. Each of them, they have a specific name. In fact, this is, I think it has got a two-stage simulation. You can just see that after it is released, the fins will open up. You can see that. So the whole simulation was done in two stages. With the initial fin configuration, it was released, and in between the simulation was changed with the changed configurations. You can just observe. After it's released, the fin is released. Fin is deployed. Okay. So then we come to the final topic. I was talking about the whirl flutter characterization. This is a GA-10 aircraft developed by an Australian company. So they wanted us to qualify the aircraft both for the regular structural flutter condition as well as the whirl flutter conditions. So in fact, we took all our instruments to Australia, we conducted the GVT there, came back, and then we processed the results, and based upon that we qualified the aircraft. So here the propeller part also was instrumented to capture the eigenvalues and eigenvectors. So based upon all the calculations were done, and we computed, so basically we plotted again the VG-VF plots, based upon which we looked at the flutter characteristics and cleared it. So coming to the final words on the presentation. So we looked at the various methods available for us to compute the dynamic and aeroelastic characteristics of the aerospace structures. We looked at the various methods available. We also looked at the various aerodynamic models available, which we are using in popular aerodynamic models available, which we are using. And we also looked at the various techniques like the finite element based technique, GVT based technique, then FSI based techniques. And in fact, the whirl flutter was done based upon the classical calculations. We didn't use any FEM there. It was a typical 2-degree freedom of freedom system, which we solved using the MATLAB equations, and we gave the solutions. So various techniques we looked at that we are using for qualifying our aerospace structures. So these are the acknowledgements, and thank you very much for your kind attention.